Well, good morning, everybody, or afternoon, depending on where you are. Welcome to the presentation, the webinar this afternoon from Kortzelek. If I may introduce myself, I am the Business Development Manager, and today's training will be the topic of generator partial discharge and the causes of partial discharge. The presenter for this session is Wojciech Betlej, who has a wealth of experience in the design and fault finding of turbo generators, and he's working with us in the engineering team at Kortzelek. Before I hand over to Wojciech, I want to make you aware that you can ask questions during this webinar, but we will handle the questions at the end, and you can do this by using the Q&A function on the webinar page. Also, during the webinar, we will be conducting some polls, and these polls are designed to help us design the webinars better and also to find out the kind of services that you need as users. So, that's the introduction, and now I will hand over to Wojciech for today's presentation.
All right, thank you, Steve, for that. Welcome, everyone. I hope you're keeping well during these special times, I would say. Let's get on with it, yeah? So, do you know what it feels like to lose everything you have worked for? And I mean worked hard, really hard. I want to start with this little story that happened in my life when I was a teenager. I used to practice swimming. It's a great sport for those who can't sleep because you have to wake up early in the morning. And it requires trainings twice a day. But because that was more than 20 years ago, at the time, when we wanted to measure our pulse, you put your two calibrated fingers on your throat, measure number of pulses for 10 seconds, you then multiply that value by 6, and magically you end up with the value pulses per minute. And also around that time, you might be familiar with that name, the company named Polar. They released one of those magical watches with the chest strap. So you put or you place that strap around your chest, and by doing that, you could accurately measure and monitor your pulse. Around that time, I've been practicing with one of my friends. His name was Marcin. He was a very talented guy. And one of the exercises was to swim very fast and then measure the pulse and measure how long it's going to take for that pulse to go down from the very high to the rest pulse, which is around 120 beats per minute. So when Marcin finished the race, he put the chest strap on and we were looking at the watch, and the pulses were 190, 170, 50, and at some point we've noticed that his pulse was jumping up and down. So obviously we started to worry. Marcin ended up going to the hospital, and he had a heart surgery. But what's amazing and beautiful is that the doctor told him that if it wasn't for that little monitoring device, we wouldn't know that you have a heart problem and you wouldn't have that particular surgery, and maybe you wouldn't be alive in a few months' time. So he was very lucky. And obviously today, we all have access to those beautiful watches. You can buy one for a few pounds or dollars. You can probably order some from China. They can not only measure your pulse, but also number of steps and more. And why am I saying that? Well, because today, our generators are usually monitored using RTDs or thermocouples to measure the temperature of the stator winding, or I presume many of you will have measured vibration of the shaft, and yet there's many more things you can monitor that can save your generator and probably have a lot more value, diagnostic value, than those two I mentioned. So we're going to start with poll 1, if you don't mind. I will start that poll. And if you don't mind answering the questions, I would appreciate it. After that, I will show you the results. So the question is, what do you currently monitor online? Stator winding temperature, rod of sharp vibration, partial discharge, and then at the bottom we have an option, none of the above. I'm going to wait for 10 seconds before I give you the results. Okay, 2 more seconds. And here we are. So these are your answers. I think they're in line with what I just said. Most of you, actually vast majority of you, would measure stator winding, rod of sharp vibration, and it's only 20%, so, well, 1 in 5 would measure partial discharge. All right, thanks very much for participating, and we're going to continue with the presentation. So, generator partial discharges. Let me start from the definition. I guess many of you know what partial discharge is, but let me read that for you. So a partial discharge is an electrical discharge that partially bridges the gap between conductor and earth, occurring between layers of insulation or insulation and a conductor. So it's called partial because it doesn't connect your copper with the core. It's part happening in between the insulation. And this is quite an important slide, and I want you to focus for a minute on that red bit. It says that the electrical strength of air at 1 bar, and when I say 1 bar, it's usually the ambient pressure. So the electrical strength is around 3 kV per millimeter. What it means for you guys is that if your machine rated voltage is more than 3 kV, you will have partial discharge, full stop. That's physics. What we can also see on this slide is that electrical strength of the materials that are used to insulate our stators like mica or epoxy is very, very high, way higher than the electrical strength of air. As you can see, 118, 300 against 3. So that's clear that if you have partial discharge, it will take place in the air rather than in the material itself. So this is the important bit that you need to take away from that slide. Now, the most important bit for you as an operator is to understand what causes degradation of your insulation system. In English, we call that TIN, and it's thermal, electrical, and ambient, as well as mechanical impact on your insulation system. And over the next few slides, we're going to go into details and explain what I mean or what's behind the thermal, electrical, ambient, and mechanical. All right, so let's start with the thermal. So thermal degradation is nothing more than oxidation, which is the chemical reaction. At high temperature, the molecules will start to vibrate. The chemical bonds occasionally break due to the thermally induced vibration. And because of that, the insulation becomes brittle, lower mechanical strength, and less capability to bond the tape layers together. I think that's clear, and it's also physics, so you can't get away from this. Now, add AC current flowing through your stator and 50 Hz. So it's not only vibration caused by temperature, but it's also vibration caused by the field, magnetic field that is around the stator. So combination of those two will quickly deteriorate the insulation system. The pool said that, well, most of you would measure the temperature of the stator winding, which is great. Again, it's one of those things that you should be doing. What you need to remember is that RTDs and TCs show temperature around 5 to 20 degrees lower than the copper temperature. So we can conclude that the deterioration happens faster near the copper conductors rather than on the outer layer of the insulation system, which sits next to the core. Then let's jump to the electrical influence. So any transient condition, so say you have an air fault near the generator and you have very high currents flowing through the stator, this will obviously quickly deteriorate your insulation. And obviously things like partial discharge, like you see on the right hand side, and we're going to talk about partial discharge a bit more further down the line. Ambient. So you can see very dirty stator. It's full of contamination. It's very unfortunate that usually that contamination that you find inside your stators is conductive. And just to show you the influence of contamination, have a look at this slide. So on the left hand side, you have a partial discharge pattern that was taken right at the beginning of the generator outage. Look how high it is. Then during the outage, our engineers performed cryogenic cleaning. And at the end, we repeated the same partial discharge test. And you can see a major difference in PD value between this graph and the graph on the left-hand side. So yes, contamination will impact your insulation and partial discharge. All right, mechanical, that's an interesting bit because we're going to talk about electrical machine, and yet mechanical influence will damage the insulation also quite fast. What I want you to focus on that slide is the pictures that show how deep the stator winding sits in the slot. So you can see that step between the bore of the stator and the top surface of the top bar. And on the second picture, it's not as deep, but also deep enough. Why am I saying that to you? Well, have a look at this slide. So, if this is your rotor, that line, there is your air gap, and this is your stator, top bar and bottom bar. And the red lines here is the main flux that's coming from the rotor through the air gap into the core. And because the stator bars are sitting quite deep in the slot, you can see that the line of that flux doesn't touch any of the stator bars. And this is what, as a designers, we want to achieve. Now, let's see the scenario when the stator bars don't sit as deep as the example on the left-hand side. You can see here that the magnetic flux will be passing the top stator bars, causing that side-to-side vibration. And that mechanical vibration will obviously deteriorate your insulation. Now, let's come back to the primary school. Well, you might remember that if you have a current flowing through the wire, around that wire, you will have a magnetic flux. So that's simple. Again, back to the physics. So now let's consider the stator being on load. So the current will be flowing through the stator winding. And because of that, you will have that flux around each and every stator bar. And that flux will cause vibration both on the bottom and on the top stator bar. And you can see it here. I think it's quite clear. Now another mechanical influence. So the influence of the 100 Hertz. Or in case of United States, you're talking about 120 Hertz. So this is generator cross-section. This is your generator core. Now, we just quickly draw stator winding. So these are your coils. This is the stator bore. We're going to put the rotor inside, and the rotor is nothing more than a magnet, or to be precise, electromagnet. And that electromagnet will produce the flux, the main flux. And obviously that flux will go through the air gap into your core and around. And because of that main flux that is rotating 3000 RPM, your stator housing and stator core will go slightly oval at 100 Hertz frequency. And it's very unfortunate that natural frequency of the stator end winding is also close to the 100 Hertz. So you might end up having problems with the end winding vibration, therefore quick insulation deterioration. I think that makes sense. And these are the pictures showing you the influence of 100 Hertz vibration in the end winding. So you can see signs of vibration here and there. All right, now, that's actually a funny one. What if I told you that the mechanical stress is happening and the winding is vibrating against a rough surface? And when I say rough, I mean something like sandpaper, as you can see on the picture. That would be a surprise, wouldn't it? Well, unfortunately, the stator core, it's nothing more than thousands of sharp knives that are constantly damaging your insulation. And when I say sharp knives, this is what the core is like. Can you see it? You have thousands of laminates. Obviously, we try to cut them as perfect as possible. But again, in life, nothing is perfect. So you're going to see some sharp edges in the slot section. And as the stator bar vibrates in the slot, it will damage the surface of the stator bar. And this is what it looks like, guys. These are stator bars removed from the machine that suffered from very high PD. Just a few more examples. Yeah, it looks very nasty. So yeah, I think at the end we can all agree that the team stresses kill your machine every day. Again, just two examples of the machines and generators. And for those two machines, it's already too late. These two machines have signs of very high partial discharge activity on the surface of the stator bars, and these operators ended up having a stator rewind. All right, pool 2, guys. Little break from listening to me. If you don't mind answering that question, so the question is, have you ever had loose wedges? In other words, during the major overhaul, have you ever had to re-wedge the stator because some of the wedges were loose? Give me some answers. In seconds, I'm going to share the answers with you. All right. Now, wow. So 7 out of 10 say that you had loose wedges. That means that most likely, if you have loose wedges, your stator bars would be or were already vibrating in the slot, causing potential partial discharge problem. All right. Thank you very much for that. And let's continue. So is there anything else other than team that causes problems? I would say yes. So if you have badly designed winding, you might end up with partial discharge problems. That's quite obvious because you have examples of that winding here on its top pictures. If you have clogged coolers or cooling ducts, as you can see on the bottom picture, this is a piece of rug that we found in one of the stators. That was probably left from the previous outage. But because of that, you will have much higher temperature in that particular location, and that will cause much faster degradation, thermal degradation of the insulation system. Poor winding quality, again, depending on where the winding was manufactured, you might end up very poor winding. And then global VPI technology. It's very unfortunate that those who operate global VPI machines will have problems with PD, and the likelihood of having those problems is very, very high. All right. Okay, so we have two more questions. If you don't mind helping me answering those questions, so do you perform offline partial discharge diagnostic tests? And please bear in mind, I'm asking for offline tests. So when the machine stands still. All right, just 5 more seconds, and I will share the answers with you in a minute. All right, so well, I'm happy to hear that more than 60% of you perform offline partial discharge, which is great. It's really good, and I'm happy to hear that. And it's only 36% of you that don't perform PD. And just one more question. Do you operate global VPI or air-cooled generator? So answer A is GVPI, air-cooled, or none of the above. It's 5 more seconds. It's interesting. All right, I'm going to show you the results. So look at this. Only 12% of the listeners today don't have none of the above. So that means that 20 or 1/4 of you is operating global VPI machine where the likelihood of PD is very high. And then air-cooled machine means that anything above 3 kV cause problems. Okay, take that on board. Thank you very much for helping. And come back to the presentation again. So I asked whether you perform offline PD. And again, I think it's great that you do. Offline PD, TAM delta, IRPI, these are tests that you should perform. But have a look at this and think about it. If you perform an offline test, you only show partial discharge coming from the electrical stress. That's it. If you, however, perform an online test, you have an influence of the team stress, mechanical, temperature, that will obviously influence the value of the partial discharge. So you could argue if the offline test gives you a full picture. If you also perform an offline test, you're going to have to use an extra source, a high voltage source. And when you do that, what you need to understand that you apply the test voltage across one of the stator phases, and the whole phase will see the same, say, take a V test voltage. If you, however, perform partial discharge test online, it's only part of the phase that will see the high voltage, because the other part that is connected to your star connection will be close to zero. So again, we could argue whether an offline test will give you a full picture on the PD activities in your machines. Okay, few examples. I think you're going to enjoy those slides. So do you remember when I said earlier that the temperature near the copper will influence degradation of insulation much faster? So have a look at the bottom right-hand side picture. This is the copper. We remove the insulation, and you can clearly see that the insulation is delaminated. And the remaining pictures show you delamination going on in between the insulation layers. And if we understand, we come back to one of the slides, we know that partial discharge likes the air, because this is where the partial discharge occurs. You can assume that there's a lot of things going on in between these layers. Now, focus for a minute on that big picture. So what you see here is the slot exit and the stator bar coming out of the core. And in that location, you have that overlap from the semiconductive paint and then with the stress grading paint. This stress grading paint, you can see on the left-hand side, is there to make sure that the potential level comes from high voltage to zero in a controlled manner. Again, quality of the insulation system, you can actually end up having partial discharge in that location when you have connection between two finishes. And what's amazing with the current state-of-art partial discharge equipment, that you can see, looking at the pattern, you can see where is the highest partial discharge value. And from that graph, you can conclude that the partial discharge is in that location at the slot exit. I would say that's amazing. Now, bear with me, guys, because I like this movie. This movie was recorded in our manufacturing facility when we manufacture stator bars. And we're going to show you the influence of the stress grading paint. So this is the stator bar without the stress grading paint, and we apply the voltage. And see what's happening with that electrical arc. In a minute, you're going to see carbonization going on here. Yeah, it's burning through. Yeah, can you see it here? It's tracking. And bang. All right, so that was without the stress grading paint or tape. Here you have another example. On the right-hand side, you have stress grading tape. On the left-hand side, you don't have that tape. So see how clear that side is. And see what's going to happen on the left-hand side. And bang! Beautiful. I like this. All right, I think you have now full understanding of why you should have stress grading coating on your stator. All right, another good example. This is a partial discharge between two adjacent faces. This is the location when one of the stator bars will have the highest voltage potential, which is the rated voltage of your machine, divided by square root of 3. And then the adjacent stator bar will have potential 0. And you can see two examples. Let me just find a pointer. You can see two examples here and there where these two stator bars suffer from partial discharge. And again, what's amazing today is by looking at the partial discharge pattern, you can say where that partial discharge is taking place. Like here, you can see that little cloud. Again, amazing stuff. All right, I like those pictures because this is where the partial discharge occurs more often. So this is the surface of the stator bars. And you can imagine when everything vibrates, as we've discussed with the team, that surface that was supposed to have semiconductive paint has been damaged, causing partial discharge to occur. And here on the left-hand side on the top, you can see the stator bar with the earthwork. So for that particular stator, it was too late. Unfortunately, this particular customer ignored very high partial discharge and ended up having an air fault. So now we talk about development of partial discharge, because we all know that when you monitor partial discharge over time, this is the key to analyze it. So this is in the lab, so you can actually age the insulation in a controlled manner. So if you focus on those blue little dots, you can see that slowly partial discharge is growing over time. And at some point, it goes exponential. Then when the insulation is carbonized, it goes almost down to 0. And here you have a breakdown. So this is what we are looking for when you monitor partial discharge on your generator. You want to make sure that you know where that exponential becomes present. And in real life, this is what you would see on a partial discharge equipment. So this is July 2013, then January 2014, and May the same year. You can see an exponential increase of partial discharge. So you do want to do something about it, because sooner or later you're going to end up with an air fault. So be careful here. All right, another good movie. So this is what we call treeing effect. So what you see here, the gray cross section here, is the insulation. In the laboratory, we introduced little flaw in the insulation material, we then applied the voltage, you're going to see the development of the treeing up to the moment when the insulation breaks. And along with the development of that treeing, you can have a look here on that orange graph, because you can see the increase of the partial discharge, the sudden drop before it goes bang. So have a look at this. You can see treeing growing. Now partial discharge, it was at its peak, and we already see carbonizing insulation here. So effect is up to the earth fault. All right, let's continue. Now, online monitoring, and for those who don't want to listen to the commercial break, please bear with me. It's just 2 slides, but I need to go through that. So what is it when you want to measure partial discharge? All you have to do, you need to have a sensor installed on every face of your stator, and then you have BNC cable going to what we call LiveView PDA2. And this equipment will constantly monitor and measure partial discharge activities, giving you a graph and progress of the partial discharge. If you, however, want to have the same view anywhere in the world, you can either use LAN cable or Wi-Fi, although very unlikely that your IT will allow you to use Wi-Fi because of the safety reasons. But it's simple as that. And something that you need to remember, that in order to install partial discharge sensors, you don't need to open the machine. All we need is the access to the terminals. And this is just an example of the partial discharge sensors installed. On the left-hand side, you can see that small partial discharge sensor, which is connected to one face. And on the right-hand side, you can see LiveView PDA2 already installed on one of the generators. Indeed, it's as simple as that. And the last slide for today, gentlemen and ladies. Why should you monitor PD? Well, out of all monitoring systems available, including your thermometers or vibration, we can say, based on the insurance data provided to us, that more than 60% of generator breakdowns come from breakdown of the stator winding. So if I was to choose only one monitoring equipment, it would be online partial discharge. All right, and with that I want to leave you. We have last question, last poll. If you mind helping me with that one, it's, would you like to further discuss an online partial discharge monitoring system with us? You can say yes or no. It's just an information for us. It's a commercial information, so we would appreciate your support. All right, well, thank you very much. I won't be sharing that with you because it is a commercial information, but thank you very much for the input and your support here. All right, now it's time for questions and comments. Steve, please help.
Yes, thank you, Wojciech. Thank you for that fantastic presentation. We do have 1 or 2 questions from the webinar participants, so I will start with the first one. It's asking whether we do have flux probe monitoring devices.
Oh yes, indeed, we do, and please apologize, I will come back to this slide. So PDA2 LiveView can combine partial discharge as well. You can, I didn't mention that because that's not part of this presentation. You can also install Flux probe and connect it directly to the same software, to the same box. So yes, we do have that solution.
Thank you for that. And the second question is, can you explain the difference between global VPI and VPI? I think that maybe some people did not.
Yes, it's a good question. Yeah. So VPI is nothing more. Well, let me explain the difference between resin reach and VPI first. So resin reach, you have a tape, an insulation tape that is already full of resin. So you tape the copper and then you cure everything together, become a solid piece of material. If you, however, use VPI, you take the same tape but without content of resin. You put that into, let's call it a box full of resin, then you suck the air out of that box, and theoretically the resin should enter every empty space in between the layers of the insulation. Now, if you have global VPI solution, this is where you wind the stator with the dry winding, so the winding without content of the resin, and you put the whole stator into a big tank full of resin, and again you apply the same solution. So you dip it, suck in the air, hoping that the resin will go into every available air cell in the winding. So these are the main differences. What I could emphasize, because maybe I didn't mention that or I wasn't clear enough why global VPI is so critical. Just think about it. So you have a machine that everything is glued together. So you have copper, insulation and core stuck together using that resin. What we need to remember, every time you start and stop the machine, everything expands and contracts. And because all these materials have different thermal coefficients, you will have copper expanding much faster than the core, for example. So is losing bone, and when you have that on PD, it's obvious. It will just happen, and we've seen that a lot, unfortunately.
Thank you, Wojciech. Just a couple more questions. Can we confirm that two important factors that contribute to partial discharge are due to the design of the insulation and the space between the slot and the winding?
Yes, indeed. Yes. So very good question. So when you wind the machine, you want to pack this machine, the slot, so the gap between the stator bar and the core, you want to pack it. You would also use ripple springs to make sure that if you have any vibration, it will be absorbed by the ripple spring. So hopefully over time, the stator bar will not be damaged when it's vibrating inside the slot. So, but having said that, I recall very recent repair we performed in one of the power stations in Europe when our winders removed the wedges and the side packings just fell off from the top slots. So you think that it's fully packed, and yet we are just human beings, so people can make mistakes, and we've seen that even recently when I was on site. Yeah.
Okay, we have one or two more questions still. Is there a solution to cure the problem of partial discharge damage in the long term? And I think this is wondering whether we can do this without removing the winding.
Good question. So, well, the situation is rather easy when it's in the overhang. So if it's the partial discharge that I mentioned at the slot exit, yes, we have repair solutions for that, and that's quite easy. If you have a partial discharge between phases, again, yes, we have solutions because we can add additional packing blocks and insulation components in between to make sure that PD is not happening. It's a lot more difficult when you have partial discharge activities in the slot. What we try to do, and again, it's just a temporary solution, we would try to inject the semiconductive varnish in between the core and the stator bar in order to recover the surface of the stator bar. I say it's a temporary solution. It's better than nothing, I would say, but ultimately you should, when you have that problem, control PD activity. Hope that makes sense.
It does to me. Another question, global VBI generators have higher PD level regarding non-global VBI. Is that correct? Is that always
Yes,
correct?
I think it's the right assumption. So after what we've seen, based on our experience, we've seen a lot more stators being rewound due to PD activity on the global VPI machines than on the resin-rich machines. Yeah.
Yeah. Okay, and the final question that I can see here, what is the maximum distance for the installation of the couplers to the generator output terminals?
Okay, so so the maximum. Okay, so maybe the distance. Let me come back to that slide. I hope you still see it. So the maximum distance between your sensors and live view PDA2 is 20 meters. So this is the maximum in between these two. If then you would like to further transfer the signal to your control room, for instance, then you would have to use LAN cable or some other protocols. But the BNC cable, the maximum length, let me just repeat, is 20 meters.
Thank you. I think that the question might have been asking us to confirm that we have to fit the couplers at the terminals themselves.
Oh, well, yes and no. Ideally, yes, but then bear in mind that the creepage distance between the sensors and the terminals must be enough. So we found occasionally, it's very rare though, but we found that the terminal box didn't have enough space for couplers to be installed. So all we do, we just put a little box next to the terminal box with the couplers installed and just connect the cable, the BNC cable, onto the stator terminals. So yes, it's a good question, and occasionally you might require an extra box being next to the terminal box. Thank you for that question, very good one.
Okay, Wojciech, thank you very much. I think that's all of the questions I can see, and I want to say thank you to everybody for attending this webinar, and we hope that you have all enjoyed it and learned some good new knowledge. Please feel free to contact any one of the three people that you see there on the screen, and we will be very happy to talk to you about any electrical machine issues. So once again, thank you everybody, and goodbye. We will close the presentation.
Thank you. Goodbye.